Hello. It all started off with overlaying the computed position of the various stars, the sun, and the moon on top of images taken from my skywatching project cameras. And this little project ended up taking on quite a life of its own. I added different modes like showing the azimuthal equidistant projection map like this and plotting where the sun, the moon, and the stars should appear directly overhead if the Earth was flat. That did not seem to correspond to real world observations. Then I added other projections such as the South Pole azimuthal equidistant, the Lambert equal area projection, the equirectilinear, the Mollweide projection, and all of these projections had some serious problems. None of the observations that could be made really made any sense. And I thought maybe I should look at one more projection, which is the globe projection. So what I did here was I took the equirectilinear projection map and I applied a little bit of mathematics to it. So the first thing that I had to do was I had to be able to generate a background based on whatever latitude, longitude, coordinate was required. And so the way I did that was I generate an image of a particular output dimension that I want. Just to speed up the transformation process, I made the output image the size of the window. So the trick becomes, how do I transform this into something that appears spherical? So clearly what I want to do is I want to go and locate each individual pixel and calculate the latitude and longitude where it would be as a three-dimensional object transformed to two dimensions like this. And so starting at the y-axis, so if the vertical component of the output image is the y-axis, then the horizontal component of the image would be the x-axis. To make the calculations easier, I look at this as a Cartesian coordinate system. So everything below the middle of the image would be negative and everything above it would be positive. And so I start at the bottom of the image like this, and I've calculated a radius, which happens to be either the height, if the width is greater than the height, or if the height is greater than the width, then I would use the width. So I take the lesser of the two and I divide that by 2, and that becomes my radius. So from the middle of the screen to either the bottom or to the top, y would happen to be radius pixels high. To avoid having to calculate the sections that are outside of the circle, I use the square root of the sum of the two sides. But I know what the hypotenuse is and I know the length of one side, so I'm able to calculate the length of the other side. And so this gives me the x component for any position along the y-axis. From there, I transfer the x and the y to temporary variables. If I'm looking down along the z-axis, then the z component would be the square root of the square of the radius minus the square of the x minus the square of the y. That gives me the z component. And at this point, I now have 3 coordinates in x, y, z coordinate space. And then I apply a simple transform to rotate the y and the z values along the x-axis, followed by a separate transformation that then rotates the x and the z along the y-axis. And then from there, I recalculate a new latitude and longitude. Since the source image is an equirectilinear flat projection, I can then use the latitude and longitude that was calculated to go and calculate a new xy coordinate from the source, and then I just simply go and get that pixel and transfer it from the source to the destination. So that is how I was able to convert the equirectilinear source image into what appears to be a globe. The other part of being able to project where the sun, the moon, and the stars would be on top of this also involved a similar operation. In this case, for the globe, I'm given the ground position of the latitude and longitude in question. I then apply trigonometry to convert that into an XYZ coordinate system. And I only have to transform to match the latitude. I'm able to match the longitude during the initial transformation process by adding the longitude in question to the longitude of where I'm looking from. And then from there, I'm able to transform that back into an XY coordinate system by ignoring the depth dimension to flatten it out into where it should appear here. So now I'm able to do a few very interesting things, such as show where the sun currently is, show its path in the last 24 hours. Dotted purple line happens to be the ecliptic, so show the path of the ecliptic as well. That is where I am, and these are where all of the stars are. In this case, I've chosen to show as the background image the view of the spherical Earth with my position centered in the middle of it, and I only have to calculate that once. So when I go ahead and back in time, you can see here, I don't have to redraw or recompute the background image. I can go ahead by day and show how the sun moves back and forth. And if you look very carefully, you'll be able to see the purple line kind of rotate around the Earth. And there's another feature that I added, which is I can show how the stars would appear if the stars were painted onto a shell outside of the Earth, like the celestial sphere, by making the Earth itself appear a third of the size. And it also helps to speed up performance, and you'll see why in just a second. But I can zoom out like that, and now I can even see the stars that start to go back around behind the Earth. And in this case, the bigger stars are in front of the Earth and the smaller stars are behind the Earth. And it's kind of hard to see, but there's Polaris right there. It's pretty much staying in the middle and everything is rotating around it like this. And if you look carefully, this smaller star is going to go behind the Earth and disappear, and it'll come back out over here. This bigger star will go to the outside and then come back as a smaller dot. There's that smaller star that just came out on the other side. In this case, I can change my location and it will alter the view of the Earth. So I can go more towards the equator. And as you can see by doing that, everything flattens out a little bit. And I can also change my longitude like that. I should be directly overhead of Null Island. And as everything rotates around the Earth, you can see that the ecliptic is shifting. And throughout the year, you can see that the sun moves in a circle like this, above and below. The latitude lines. Part of the reason why I added this mode was to also let me see what the Earth would be like from the vantage point of a given object, such as the sun. And as I go ahead throughout the year like this, you can see that the sun appears to be looking down towards a higher latitude. Then it slowly comes back down south towards a southern latitude like this. And then throughout the day, everything remains relatively constant, except this is the location of the observer projected out onto the celestial sphere. So as the Earth rotates, this rotates around the celestial sphere as well. And the moon slowly drifts across as well. And the last thing that I wanted to show, and was one of the main reasons why I added this mode, was I wanted to see how the magnetic contour lines looked when projected onto a globe. And I found an algorithm that calculates the magnetic declination for any location on Earth. And I tried a few times to come up with an algorithm to draw out the path of a specific magnetic declination, but it wasn't quite as simple as I wanted it to be, so I kind of left it aside. And instead, I just opted for a whole series of dots. And if I remember correctly, this is based on some other contour line maps that I've seen. I think the blue is declination towards the east and red is declination towards the west, but I might have those two mixed up. But the nice thing about this, even though it is very slow to process, I can see what the magnetic declination lines look like when projected onto a sphere. So that's what it looks like from the North Pole, South Pole, that's above Null Island. And that's what it looks like at 90 degrees east, 180 degrees west, and 90 degrees west. And at this point, I'll create a few animations that show what the Earth looks like for the next 48 hours. Then I'll cycle for the next calendar year after that from a fixed position and from the view of the sun. So that's going to be it for now. If you like the video, I would certainly appreciate the thumbs up, the subscribe if you're not already subscribed, all that other good stuff. And I'm going to see you again in another video soon enough. So bye for now.